So hello everyone, this is lecture 28 for the electricity and magnetism. In the last lecture we were discussing about the self-inductance and we discussed these three cases, the coaxial cable, the solenoid and the coils. So let's see one more case, that is our toroid. So here we will see the two cases, first for the circular cross section, then we will see the rectangular cross section. So first circular cross section, for that first we need to see what is the magnetic field inside. So for a toroid, magnetic field is given by mu naught n by 2 pi r. We already derived this. Now to find the total flux, we need to check for the one circular flux, so that will be B cross A, and for the n turns it will be n. So just put the value of B and n and A, it will give you mu naught n square A by 2 pi r I. So this will be your self-inductance L. Now let's see for the rectangular one. So here this time we have cross section as rectangular and this height is h and this radius is A and this is B. So we need to integrate. So first we will see that what is the flux through this small length. Let's take it out like this. So this is dr and h. So hdr will give you a small area. So first we will see the flux from this area, then we will integrate this from the A to B to find the complete flux. So inside the magnetic field will be mu naught n by ni divided by 2 pi r if this distances are from here to the center. So this is your magnetic field in the tangential direction. Now the magnetic flux will be gained by this area is hdr, and now we'll integrate this dr from A to B. So integration will give you mu naught nih 2 pi log b by a. So this is your magnetic flux, and now take this I out. This is the magnetic flux through the one coil, and for the n coil just multiply n here, so it will give you n square h 2 pi log b by a. Take this I out, so whatever remaining will be your self inductance, so it will be Li. So that's how you find the self inductance for different cases. So let's start the new topic, that is Maxwell's equation. So see, Maxwell's equations are just what we studied up to here. That is, first equation is nothing but the Gauss law. So that is del dot E. Divergence of E is given by rho by epsilon naught, and in the integral form we can write it as E dot D equal to total charge enclosed divided by epsilon naught. And here we will write this equation for the time varying fields. So what is the meaning? Means fields are changing with time. So second equation is given by the divergence of B is 0 and B dot D equal to 0. That is also Gauss law for the magnetostatics. And now the third is nothing but Faraday law. So del cross E equal to minus del B by del T, and integral form will be E dot dl equal to minus del B by del T dot dA. So these are the three equations. Now fourth is nothing but Ampere's law. So first, before studying these equations, let's see what we know about the Ampere's law. So that is del cross B equal to mu naught J. So this is our differential form, and the integral form is B dot dl equal to mu naught I enclosed. So this is the Ampere's law in the integral form, but this is valid only for the static field only. Means when the field is not changing with time, only then this is valid. And we can see that case. Just take the divergence of this equation. So this will divergence of curl must be equal to 0. So means divergence of J must be 0. So see, this will be 0 only when J is steady current, means J is not changing with time. So that is the case only for the static field only. So that's why this equation is valid for the static field. Now see that it is not the ideal case, means not always we have the constant electric current or the static field. So we need to consider the time varying field. So in general, the equation del dot J is given by minus del rho by del D. Now let's see what how this expression changed this expression, and that is given by this expression is changed given by the Maxwell, and that's why this fourth equation is given by Maxwell, the modified Ampere's law. So let's see how this will be modified. So del dot J equal to minus del rho by del T. From the first equation, rho can be written as epsilon naught del dot E. So it will be epsilon naught del dot E. And now just this del is operator and this is also operator, so we can take this del out. So it will be del dot epsilon naught del E by del T. Now take this side, so it will be, take the divergence common, it will be J plus epsilon naught del E by del T equal to 0. Now see, in place of J, it will be, complete equation is this must be equal to 0. Means if time means field is steady current or field is static, then this will be 0 because it is not changing with time. So then you will get the same equation again. So that's why this is the ideal case. And now this is the current density, and this is also current density. So we call this current density as the displacement current density. So this is the new term added by the Maxwell. So JD is defined as epsilon naught del E by del T, and now from this we can define the equation again. So in place of J, we will write J plus JD, and that will be mu naught J and mu naught JD. So mu naught JD will be mu naught epsilon naught del E by del T. So the new equation will be del cross B equal to mu naught J plus mu naught epsilon naught del E by del T. So this is the modified Ampere's law, and this is the correct definition. It will be valid in all the cases. If field is not varying with time, this will be 0 and will give you again the Ampere's law. So now the integral form of this can be written as b dot dl equal to mu naught I enclosed plus mu naught epsilon naught del E by del T, and this is dA, this is surface integral. So you must remember this equation. This is your fourth Maxwell's equation for the time varying fields. Now let's see how, means here we can see the change in electric field producing the magnetic field, and change in the magnetic field producing the electric field from the third and fourth. So these are the equations. Let's see in the physical cases that how can we visualize this, the change in electric field produce the magnetic field. So let's see. For the case of capacitor, means charging and discharging of capacitor, we can see there that change in electric field produce the magnetic field. So let's see. This is your capacitor plates, and this is your battery, and this is your switch. So when we place the switch, then the current will increase rapidly, and means this will charge the plates. So when the time that these plates are charging, then the electric field between these plates will change. So we need to check that if there will be any magnetic field due to that or not. So when this is charging, then charge is changing with time, and here also charge is changing with time. So there are 2 points. This is outside these capacitor plates, this is inside these capacitor plates. So let's find the magnetic field outside and the inside at these 2 points. So first, the electric field between these plates is given by, we know, between the capacitor plates it is given by sigma by epsilon naught. So sigma is nothing but charge per unit area, that is q divided by pi r square epsilon naught. So at point 1, so here we will see if we make a complete loop, so only this I current is passing through this, so we can use the Ampere's law. So that will be B multiplied 2 pi r, this radius is r, so equal to mu naught, and current is I, plus the change means del E by del T will be 0 because there is no electric field changing, so it will be the other part is 0. We are using this equation. So here this del E by del T will be 0, means this equation we are using, so del E del T by will be 0, and only this will equation valid. So del E by del T is 0 and I enclosed is I, so B 2 pi r equal to mu naught I. From here B will be mu naught I by 2 pi r, and is in tangential direction. So this is your magnetic field at this one point like this. Now we need to find the magnetic field at this 2 point inside this, means it is in between these capacitor plates. So at point 2, I enclosed will be 0, means there is no net current, net wire is passing through this, so I enclosed will be 0, but there will be change in the electric field, so only the second component will take part. So del E by del T is nothing but, we just take the rate of change of this, differentiate, del Q by del T will give you current, so it will be I by pi r square epsilon naught. Now from here B 2 pi r equal to this mu naught 0, and this will be second term, so we are using this equation again, this one. So this term will be 0, now this will be working here. So it will be mu naught epsilon naught multiply I by pi r square epsilon naught into pi r square, this is the area, and through which the electric field is changing. So from here this will cancel out, and mu naught will be as it is, and this is I, so equation will be solved to this, B equal to mu naught I by 2 pi r and the phi cap. So this is your magnetic field, and see this is the same as we find at the first point, so this will remain same. Now see there is no net current passing through this, so how we are getting this magnetic field? Due to the change in electric field. So this actually verified the results we got, that change in electric field produces a change in magnetic field. Now this is a case when this point is outside. Let's take some loop inside these plates, like here when r is very small than capital R is radius of this capacitor. So loop is here, so we need to find the magnetic field inside. So here just a change will be in place of pi r square we'll write small pi r square, so that will give us expression for B will be mu naught I r by 2 pi r square and a phi cap. So see here magnetic field inside the capacitor plates will be changing proportional to r, and outside it will be changing inversely proportional to r. So the graph will be like this, up to capital R it will be like this, and after R it will be like this. So that's how your magnetic field will change. So must remember this, can be asked in the exams. Now we will see the Maxwell's equation inside matter, means these are the vacuum cases, but when it is matter, means you can have the magnetic material, you can have the dielectric material, then how these equations will change. So see, we already studied about displacement and the H field. So displacement vector is nothing but epsilon naught E plus P, this is the dielectric case when the polarization is take place. So D is nothing but epsilon E, and B is mu naught H plus M, so B is mu H. So we studied these cases. So first equation will be changed to this. We studied that D vector is depending on the free charge only. So del dot E equal to rho F, and the integral form will be D dot dA QF. So this is your first equation in the matter. Second and third equation will remain same, but fourth equation will change. So how the fourth equation will change? Now see, you have some material and you are seeing that electric field is changing. So when electric field is changing, then polarization will change, P vector will change, and when P vector will change, then charge distribution, the bound charges distribution will change with time, and that will give you a current, because charge is changing with time, that will give you current. So that will be because of change in polarization or change in electric field. So that's why we call that as polarization current. So let's find the polarization current, and then that factor will leads through the magnetic field. So di current is given by charge per unit area and the area divided by time. So this will give you charge per unit time. So this is bound charge is changing, that's why I have taken this sigma b. So this will give you the current whatever you will get. So it will be, just take this dA this side, so di by dA perpendicular will be equal to del rho sigma by del t. Now sigma is given by, this is bound charge, sigma bound charge is given by P dot n cap. So we already studied this formula. Now see, this is nothing but current per unit area, so this is current density, and this current density will be called, because here we will get del P by del T, so we are calling that as polarization current, so we'll call it as polarization current density. So Jp will be del P by del T. So now there will be this extra factor which will lead to the magnetic field. So now in the equation, in this equation, we will write, in place of J, we will write the free current, because in the matter you will have either free current and the polarization current and the bound current. So there will be three factors will be included here. So equation will change to, let's see how the equation will change. So this time J will be, in the matter, JF free current density and the bound current density and the polarization current density. So there will be three factors included, and then the differential form will be del cross B mu naught, these three factors. Now JB will be given by del cross M, we studied this formula, and JP will be del P by del T, and plus mu naught epsilon naught del E by del T. Now see, from here this mu naught will be go this side, so B by mu naught, take here common mu naught from here also. So then there will be del cross M remaining, so del, just take the curl common, it will be B by mu naught minus M equal to JF will be as it is, and it will be, just take the del by del T, and it will give you epsilon naught E, means E will be here, del by del T is common, and plus P. So you can just rearrange this equation, this will give you this equation, and from here we know this is nothing but H. So del cross H equal to JF, and this is D, displacement vector, so it will be del D by del T. So this is your fourth Maxwell's equation inside the matter. Now the integral form can be written as H dot dl equal to I free current total plus del D by del T and dA. So this is your fourth Maxwell's equation, you must remember, inside the matter. So you must remember this. Now there is last thing here, that is boundary conditions. So we have studied the boundary conditions for the magnetostatics, for the electrostatics, and now here see that in these there are only two equations are changed, and there this area included. So in these equations, the first and the fourth, this area is come into the picture. So let's see, the boundary condition is depending on this area, and this area tends to 0, we know this. So that's why the equation won't change, means boundary condition will remain same what we got for the magnetostatics and the electrostatics. So the exactly same as the steady cases. So these boundary conditions for these cases will remain same. So you must remember these results. So that's how our magnetostatics part is completed, and the static means electrostatics and all that completed. So now in the next lecture we will start the application part. So that's it for today. Thank you everyone.